I'm going to continue today reviewing the challenges on Turing Complete. I think this is the last time that I'm gonna do the challenges. I don't think I'm gonna solve the other ones because it's too annoying and I couldn't find the solution to the last level that I stopped. So probably next time I'm just going to I think that I was thinking about this and I think that it's probably a good idea to work on trying to translate the hardware concepts that I've learned into Turing Complete schematics. So study the hardware resources that I have, use ChatGPT, and search for schematics of real hardware to translate into Turing Complete. And I think the first one that I'm thinking about doing this is a data path. That's probably what I'm gonna do. I think I have another list as well, if I remember correctly, of ideas that I brainstormed with ChatGPT some time ago, but I don't remember really well. But I think for now, I'm just gonna follow this because it's easier. Meh. Change the chat. And also because it is something that I've wanted to do for quite some time. I think it's gonna be very good. Because then it's gonna force me to build the concepts, not just read them. And I'm mainly interested on the control logic, to clarify how the control logic works. I think for today, depending on how much time it takes, I'm just gonna go over these solutions with ChatGPT. Most of them, probably all of them, I just searched the solution online or I found with ChatGPT. Okay, so this is the counter. Let's see what is happening. The level along. This is something that I didn't like about this Turing Complete. It's basically very similar to the problem I had with lead code and things like that. Is that it becomes hard to a part of the problem becomes to try to understand what they are trying to what they are asking, what they're trying to make you do to pass the level, and I really don't like that because I didn't get this game to pass levels. Just got to learn the principles. But I think that this is just inevitable to because it's kind of hard to from their point of view, it's kind of hard to explain. Not really sure if I understood there what they mean by the inputs. Sure. So based on this here, I think obviously it's gonna be the enable, but I don't know. Like that's the thing. I don't know how this is gonna fit on the bigger circuits. So I think obviously on the concept level is gonna be used on the as a program counter. I think. So to count instructions, but just looking at this here, it's kind of confusing. Obviously, like I don't understand why When the input is on, is gonna send the byte here. These ones are delays in the codes. Why is it sending it here? The problem as well with these levels is that it's starting, like, it gets too complicated to ask GPT, I think, as well. Because then I have to translate a massive circuit. Yo, thanks. What does this mean? I think about this. So, I think what this does is delay by 1 tick the input. I think that this input here is loading the value on the circuit, and then it delays by 1. So the next cycle is the one that is actually gonna save the value, I think. Not sure. This is not a programming language, it's just building hardware using logic gates. It's a game called Turing Complete. You can buy on Steam. They're cheap from what I remember. And the idea is that you build a full computer from logic gates. So each level you have to build a circuit, a logic gate, then you unlock that gate for the next levels until you build a full computer. Oh, this one can build the solution. Problem is, like, it's gonna open a video. I should think about whether or not you should ask GPT. The problem is, like, how I'm gonna ask. I can't, but obviously it's gonna take a bunch of time to explain the full circuit. I think I have to maybe just gonna ask how does a counter work. Understand why this switch here. If passes. maybe we should go over. I think I'm gonna go over the levels like superficially first, just show the solutions. Otherwise, I'm gonna spend too much time on this. Then come back. Then I think about like what questions to ask to try to understand more the circuits. Obviously, I think that is using AND and XOR because that's the pattern for adding. So the XOR does the adding, as I went over the last string. XOR adds the bits because it measures the difference between them. And on binary, whenever I have 1 plus 1, the result's gonna be 0 actually because the 1 carries over to the next thing. And that's the confusing part. So it carries over as 1 because it moves the significance. It is like adding 2. And then the AND does the part to carry the bit. Because if it was just XOR, you would lose the information. So you need the AND to carry and the XOR to do the sum. Obviously here, I think that's what it's doing, but I don't understand very well. Obviously the level, the purpose of the level should count. So I think it's probably increasing the inputs on one tick with the inputs on the next one based on this enable signal here. I think that's what's going on. I think it makes sense because the counter can, if you want to have a program counter, you need to be able to support jumps as well. So you can't count 1 plus 1 as a label instructions, I think. Now I'm gonna look to the other levels and then I'm gonna go back, then think more about it. I think I'm gonna try to ask like foundational questions, and maybe I'll go over there are some schematics that I already have there. So initially I thought that you have to solve all the levels to see the custom schematics, but then I realized you don't. And this is the part that I'm most interested on now. But I don't think I'm gonna finish the rest of these challenges here. It's just annoying. I wish they provided a solution for all of them so I could see. But it doesn't matter that much. But the custom levels are on the sandbox here. And I think somewhere here you can download them. This part is the one that I'm very interested on right now. Remember, this is supposed to be. I don't think this is finished, or there's something wrong with this one. But it's supposed to be a web server, I think, or something like that. There is a place here. Schematic hub. So here you can search for different schematics and download. I think I downloaded the RISC-V, RISC-V, which is an architecture, and this web server one, this web server here. Don't remember where I think yeah, it's here. So these are the ones that I have now. Yeah. So this is the part that I think is going to be interesting. Because then I can try to translate the data path into this and then slowly build the computers that I learned from Honor Mutlu lectures. And obviously use ChatGPT to try to help if I get stuck. I think I should build like one by one data path, then cache coherence. Another one that is very interesting, obviously, would be, which is something that I've been studying a lot, is the connection between the kernel and the modem through the NIC and the NIC driver. Like how do you build the queue? How do you build the cyclic redundancy check, which is building the hardware, basically a sum of the bits of the message to verify if the message wasn't changed or something like that. I think this is the related to physics. I'm gonna go over the campaign. Let's go over quick. And this is supposed to use the registers to save values or something like that. Can you fit 4 bytes of memory in this limited space? I'm to build a circuit that save or loads the 4 different bytes. Blah blah blah. Okay, next one. I think these are the ones that I didn't do on last time. This is logic engine. So this is basically decoding the instruction here. And then based on the decodes. Yeah, this one I understand. The other ones I don't understand very well, but this one I understand very well. It's basically you have a byte. So all the instructions are on the hardware is just bits. And the way that the hardware derives the meaning of the bits is through the control logic. So basically the way that the wires connect the impulses between the different parts of the computer determines what happens, obviously. So this component is from a previous level that you do. So here what is happening is basically this one is gonna transform the byte input is gonna split into the bits. Then you connect into the decoder, and this is gonna allow you to determine what's the meaning of each instruction. And I think on the level log that they provide. So zero bits should be the OR, and 1 should be NAND, and so on. So basically what that means is that I have the values here. So I have to transform the bits here from a bit into the meaning of what it's supposed to do. So since the 0 bit is the R, it goes into the switch. It determines when the bit's gonna be active, let's say. So it's gonna go into the outputs. And then you connect the switch to the operation you want the meaning to be related to. In this case, it's gonna be the OR. So this does the OR of 8 bits between these two inputs here. And then the other operations, so you can build all operations you need from 3 fundamental logic gates, which are the OR, the NOT, and the AND. With these 3 gates, you have Turing Complete computation because of the principles of space-time. Is union, intersection, and negation. And I think that here, the reason why you don't use the other gates directly is because it saves, you can reuse the same NOT to do the computation. So I think that's probably more effective to not use the NAND directly here, because it saves amounts of gates and wires. I think that's the case. Next one. This is where it starts to get into computer architecture. I think this the first one. So for these ones, I looked into the solution that they provide there. Basically, this one is a register, a save value. Output. So if I remember, so it's basically the coding here, like in the other one. Then it's gonna use the decoding to determine the registers, whether they're gonna save the value or load, obviously. So this is the counter that you built that I was just seeing on the previous level. And you can change here. So here in this case, incrementing by 1. But if you click here, you can change the value, the amount of bits that is gonna increase each iteration. So this is increase the counter by 1, which allows you to run the program, the instructions. And the instructions are received as bytes, and then you have to decode them. So I think that's what the level is teaching, probably. Teaching how to decode the instructions from the program and save and use the registers. Because the registers are the things that do the computation on assembly. Like they are the smallest region of memory. So it's registers and the arithmetic logic units. So the ALU is the component that is going to do the calculations, and the registers are the components that save the memory. I think this lab is teaching how to change the state of the registers based on the instruction of the program. The code's here. So this decoder is going to the save. So it wants to save the first 3 bits. And it wants to load the other ones, I think. Yeah. So first 3 bits you save, and the other ones you load. Yeah, so this is basically doing a copy. The first 3 are the source, and the first 3 give the destination. And yeah, so that makes sense, obviously. So 4, 5, 6 load into the register because they are the source, and then 1, 2, 3 save because they are the destination. So it's basically allowing you to copy the bits from 4, 5, 6 to 1, 2, 3. Yeah. Maybe this one is like, because on the other levels you use the same component, the same schematics, and then you just add circuits. So I think that this might be already like a more complex version. Yeah, I think I use the same one for all of them probably. Or maybe, maybe this one is simpler. No, this is from an old version, so yeah, I think that's I reuse the same schematics for all the levels. I think this is already more complex than just registers. So just immediate calculation. Yeah, so this is one of the components you build, I think. You can go here to see. So it's basically decoding. And what the decoder allows you to do is transform. It's basically a combinational logic. Because like you are getting the output is all the possible combinations of the inputs. That's basically what the decoder is doing. I think you can go to the decoder level again as well. So here they make you create this decoder. So the bits can mean anything that you want. So in this case here for the game, the assembly that they are creating, they are selecting these values where the 0 represents immediate, the 1 represents calculation, the 2 represents copy, and the 3 the condition for the jumps. Can't go there. Okay, so this will be here. For all these levels, I'll also just looked into the solution, so I didn't do this on my own. Okay, so I think what is happening here is that like the first level, which is the registers, you just build the register components here, which allow you to copy the bits from the first 3 to from this 4, 5, 6 to 1, 2, 3. Then on the other levels, you put other gates that allow you to do different operations on the registers. And I think that's what this thing here is doing. So I'm not really sure if you... Yeah, I think the only distinction is between these registers here in the ends and the registers in the beginning because of the decoders they are connected to. But I don't think it makes... Like I could do this logic gate here on the 5th register instead of the 4th, I think, and it wouldn't change anything. You just change the way you translate the meaning on when you're writing the program. So the second one's calculation. So that means I think here is going to be used to calculate. It's going to be the load. Oh, the save. So it saves the calculation. And here's the input, I think, the first. Oh, the opcode comes from here. Yeah, so the opcode comes directly from the program. Which means that this basically decodes the input of the instruction. And this is something that I was trying to remember as well. It's kind of confusing. But I think that is instruction, then you decode, then you fetch the instruction, then you execute, and then there's memory. That's the full data path. And then the complexity comes from reordering instructions to maximize how many instructions you do per clock cycle. And this introduces data hazards because if you write to a memory place before you read, then like it changes the meaning of the program. In order to enforce that you don't have corruption, you have to create control logic between the different levels of the pipeline so they can communicate with each other. And this is the part that I'm most interested on trying to build later, along with the speculative execution and the reservation station registers and stuff like that. So the first one is immediate, which is basically just a value going here on the first register. LAU you also build on a previous level. The thing that is kind of confusing is because like you type here the instructions, so you can create custom instructions here. And the way that you create is based on the bits here. You can see they give you the meaning. Here. So here is basically how each instruction is going to be perceived, let's say. So I'm trying to understand. Obviously, this is connected to the hardware, so it has to be. Trying to connect how this input here is gonna relate to the rest, to the circuit. And that's the part that is not very clear to me. Yeah, because in one level is the copy. And now it's saying that the bits, the first bits here determine the nature, so that's what I don't understand. Oh, I think I get it now. Let's see. Because here is gonna be 6, 2, 3, 4, 5, 6. Yeah. So I think I get it. Oh. I think what it means is that basically the first 6 here are the ones that go here on the decode to see which register is gonna be active. But the first 2 here that determine the nature of the instruction are not are the last ones here, probably. So they don't do anything on the register on this side. They just go over here and then they are decoded here. Yeah, because this is gonna take the 2-bit input, translate to 8. Hmm. Also, this is a jump instruction, probably the logic here. Yeah, it's conditional here. So because it's conditional, it goes to this end here, which activates this. And here's probably the address. Yeah, it's going to be the value of the address. So the condition is here, goes through here, which is the LLU. And so the ALU receives the instruction directly from the program. And it's going to sum, or it's going to do an operation with these two registers here, because they are connected here. Then this one goes here, is the result, and goes through the switch. The switch is determined by here, this one. I get it on the conceptual level, but not very extremely clear on the details. It's kind of confusing because of the wire. Not sure what the relationship is going to be between the things, but I think I understand. So it's basically using the LU to calculate the value of the jump, the condition. So the way that it works in assembly is that the jump, like in real assembly on a real hardware, from what I remember, you have a register that is just used for flags, and then you do a calculation between the values of two registers, and then based on the result of that calculation, you activate certain flags on the register flags. Then based on those flags and the nature of the instruction, you decide whether or not to jump and where to jump to. I think this is what this is doing here, basically. It's using the LU to calculate the label, the number of the program counter, to like determine what the instruction is to jump to. And using the register to do this register here to do the operation. But maybe he uses all of them. It depends on which ones are active, I think. That's why all the cables connect here. But it's kind of weird because only these ones are. It's weird because I know you can do the condition with other registers as well. Oh no, just these three. Oh, so there is no registers here. Yeah, so I think the condition is always going to be through the registers 2 and 3. I thought that there were registers, yeah, but it makes sense that there isn't. The first three are these inverters. It should be these ones that determine. I'm gonna go over I'm pretty sure it's only gonna be this circuit for the other levels as well. So this is just the one that I went over. So basically same principle that I went over the other one, I think. Just for adding. Yeah, so the level log gives you the what's each bit should be. So they call the bits from the input and use a switch to determine which one is active. I'm not really sure if this is the best way to do this though. Because what if you have two different it's just the values here. That makes sense. So if I have two inputs, then we're gonna have 6 there. Which means this subtract. And then it goes here and here. I think that it obviously works here because it passes the level. I'm not sure if this would work in practice because everything is directly connected to the outputs. So like I don't think that this maybe it does ensure. Yeah, I think that probably does because of the switch. Like the values of the bits here are decoded and then each switch is connected to the operation that it should be equivalent to. So this one will be the subtraction. So you add, so you do two complements. So you invert the one of the values and then you add by one. And then you sum this one here, I think. So next one. Is simple again. Let's skip over. So it's basically gonna be the same circuit, I think, for all of them. It's just builds on top of the same one. And I use the same schematics for all of them. So these other levels are very annoying, the programming ones. I'm just gonna show the solution. Because it was very annoying, I didn't want to solve. But basically here, you start using the program that they give you there to write the programs as if you're writing assembly, but obviously based on the game logic. So you can edit the instructions directly on binary. Then you can see what the instructions are meant to be here. For example, the first instruction here would be this one. So it copies input to register 1. It's basically just numbers, and then based on the structure of the gates here, is going to perform the operation based on the bytes that it receives here. So this one, the solution is just this. You change the values here to this. This one is this. I just copied from somewhere. They gave the actual numbers instead of labels. If you want to do labels, you can click on add here and then create your own value here based on this thing here. So this would be copying from register 0 to register 1. So this is the solution for this one. So next one. It just went over this. Kind of hard to. Yeah. So this one is register 0, register 1 is this value. Then input to register 2. This. Then the end 6, 7. Register 3 to out. That's the solution basically. Next one. Out 3 is this. P1. Add. PT2. Restart. Next one. Yeah, this one is just all in numbers. This one's just numbers as well. Again, each number is going to become a instruction depending on the bits there. And the way that the logic gates transform the bits. Or maybe the masking time is wrong actually. I think one of them I kind of cheated. I don't remember which one. I couldn't find the solution online, so I just put there was one video that teaches, I think is this one. No, it's not this one. It's one where you have to count, I think, or to guess the value. But all you have to do is basically put a counter here and then puts a null, and then it increments the value by 1. So I don't remember which thing I was trying to test here. Pretty easy. I remember that I went over this with ChatGPT. It said this level existed to test something. I don't remember what was the point of this. This one is to do XOR through the gates. I just copy the solution again. Register 4. Switch to register 5. Register 4 to register 1. Register 5 to register 2. True. bytes. These ones are pretty easy as well. Just do XOR on the byte level, and then it unlocks a gate for the other ones. Yeah, same thing as the other one. Checking for quality. Yeah, this one I look into the solution. I'm not really sure why. Use the XOR and the end. Yeah, so based on the truth table here, check to see if they are different or the same. So it's basically a filter. Then the end's gonna, like this one filters for sameness. So if the two inputs are the same, and this one filters for if both are true. So I think it's pretty easy. And just do on each one of the bits, on each byte, and then you get the equality. Another one that is very easy. The sign loss. I don't understand very well, but like I'm not really intrigued on how this works. Yeah. So I think I'm gonna stop streaming now. Just gonna do stuff off stream. So this is the last level that I stopped, and I don't wanna put. I tried a solution that I found online, but it doesn't work. I don't wanna put a bunch of time trying to solve this. So the next thing to do is gonna be to look into the custom schematics. I think probably I should try to do a data path without using any custom things, but it might get too difficult or too many things, many wires and logic gates. I might be forced to create custom components in this component factory. But I think I should try to avoid doing that as much as possible. So I can build everything from logic gates. shift left is the same as division, if I remember. Because dividing by 2. I don't know if they create this. There is no icon here to go to the custom component. Not sure if the game gives you this on the sandbox or if you have to create. And if you have to create, then how do I create this? Obviously, I can use ChatGPT to figure out. Actually, I'm gonna ask ChatGPT what it thinks is the highest ROI. See if it comes up with something else. This one first. So there are a lot more components available here. But I wonder if I can build them from scratch as well. I'm gonna stop streaming, so next time that I stream, I'm going to probably create this. Either I'm gonna do this the data path, or I'm gonna ask GPT off stream if he thinks that there's other better things to do first. But I think I'm gonna try to stick with one. Actually, maybe not. Maybe it's probably better to either I do on the schematics or I can do on the component factory first. And it might be better to do on the component factory first. So I build like each component of the that I'm trying to clarify. There's like the data path, cache coherence, cache consistency stuff. Then things related to the kernel, to the NIC driver and the NIC. And I build each one separately, and then I try to combine them on the sandbox later. That might be the best way to do this. Either this or I will follow the list that I have there of other projects. I think here I'm gonna ask GPT off stream if he thinks, but I'm probably gonna go with the data path. So I wanna see if I can build a data path from scratch, and I'm definitely gonna need help because I don't remember the details very well. I do remember the conceptual level of how everything is connected, but obviously like building from scratch is gonna be a lot harder, I think. So build the data path, the multiple instruction execution at the same time, and then data hazard solution, and then the speculative execution, and reservation registers. And probably another thing that should be very interesting is connecting the data path to the memory, because you have the translation look-aside buffer, and the caches, and then the RAM and the disk. So I want to clarify like the whole process. I think trying to build is going to be very good for this. That's probably what I'm going to do next. So I'm going to stop streaming now, probably very soon. Next time I'm going to try to build this from scratch. So see you then.